Yes, it's me, Mr. Ernst, here to talk to you today about the Pythagorean Theorem. This video is meant to be a kind of a review for Unit 2, which is all about the Pythagorean Theorem, and it's also got some number theory about rational and irrational numbers. So this video is actually broken into two parts. The first part is all the basics of the Pythagorean Theorem and the three main problems that it's designed to actually solve. The second video is the one that's going to focus a little bit more on the trickier Pythagorean Theorem problems, and it's also going to go a little bit more into the number theory. So let's get right into it. The Pythagorean Theorem. So the Pythagorean theorem is an interesting pattern that happens with right triangles and only right triangles. The theorem comes from the three sides of a right triangle which have special names. The longest side opposite the right angle is called the hypotenuse, and the two smaller sides that create the right angle are called the legs. The Pythagorean theorem highlights the relationship between the legs and the hypotenuse of a right triangle, which goes like this. Leg squared plus leg squared is equal to the hypotenuse squared. This theorem is used to solve three main problems. The first problem is a right triangle with a missing hypotenuse. The second problem is a right triangle with a missing leg. And the third problem is to identify a right triangle. Let's start with the first one, which is a missing hypotenuse problem. Here is a right triangle where we have the values of the legs, but not the hypotenuse. To solve this, we start by writing our equation. Leg squared plus leg squared is equal to the hypotenuse squared. Since we know the value of the legs, we can plug those into our equation. Now we can start to simplify the terms we know. 3 squared gives us 9, and 4 squared gives us 16. Then we can add the 4 and 16 together to give us 25 is equal to the hypotenuse squared. However, we're not done yet. We are trying to find the hypotenuse, not the hypotenuse squared. To remove the square, we take the square root of the hypotenuse, and to keep our equation balanced, we also take the square root of 25. This gives us our final answer, that our missing hypotenuse has a length of 5. Now let's compare this process to the second problem the Pythagorean theorem can solve. A right triangle with a missing leg. We start this problem by writing out our equation. Leg squared plus leg squared is equal to the hypotenuse squared. Next, we fill in the parts of the equation we are given and simplify the squared terms. To isolate the missing leg value, we have to subtract 9 from both sides, giving leg squared is equal to 16. However, just like before, we're looking for just the leg, not the leg squared. So we have to take the square root of both sides of the equation, which reveals that the length of our missing leg was 4. Missing hypotenuse and missing leg are solved in a very similar way. The only difference is that with missing hypotenuse, you add the two numbers, while in missing leg, you subtract them.
2 down, 1 to go. This last problem is called identifying a right triangle. This problem gives you all three sides of a triangle and asks you the question, is it a right triangle? I mean, it sort of looks like a right triangle, but without the square in the corner telling us that that is a right angle, there is no way to know for certain just by looking at it. Luckily, we have the Pythagorean theorem. Because the Pythagorean theorem only works with right triangles, we can use the theorem to sort of test these side lengths to see if they make a right triangle or not. Here's an example. We're given a triangle with all three sides. Nothing is missing. As always, we write out our equation, plug in the given values, and simplify the left and right side. The result tells us that 25 is equal to 25, and this is a true statement. These triangle sides worked with the Pythagorean theorem perfectly, so we know that yes, this is a right triangle. Let's compare this to another problem. We have a triangle with all three sides, and we want to know, is this a right triangle? I'm going to follow the same steps as before to test this triangle out. The result of this equation tells us that 13 is equal to 16. Is this a true statement? No. So is this a right triangle? Also no. Despite the fact that it looks like a right triangle, the Pythagorean theorem tells us it is impossible for these three sides to make a right triangle. Sometimes, however, the problem doesn't give you a picture, but rather just the three side lengths of the triangle and asks, is this a right triangle? Even without the picture of the triangle, this is solved the same way. The only difference is that we have to identify the hypotenuse, which will always be the longest side. Once we have that, we can set up and simplify our equation. Sometimes you are given a side length that is written as a square root. Treat this like any other number. Write the equation and plug the given values in. Squaring 2 and 6 is fairly easy, but how do we square the square root of 40? Here's the thing. Squaring and square roots are inverse operations, or in other words, they're opposites of each other. They cancel each other out. When you square the square root of 40, the two operations cancel out, and we are left with just 40, no change. When we finish our equation, the result is that 40 is equal to 40. That equation is true, which means that these three side lengths do make a right triangle. Let's look at one last problem where all three sides of the triangle are square roots. Once you understand how squaring and square roots cancel each other out, these problems become a breeze. 5 plus 5 does not equal 11, so these sides do not make a right triangle. This problem tries to make things complicated, but remember there are three main problems that the Pythagorean theorem solves: missing hypotenuse, missing leg, and identifying a right triangle. Once you recognize what you're solving for, the process is always the same. In this problem, we have two triangles back to back. They share a height of 5 and have a couple of missing pieces. Our goal is to find the missing values A and B. Feel free at this point to pause the video to see if you can find the correct answers before I go over it. To solve this problem, it is easiest to redraw the triangles separately. I'm going to start with the smaller one on the right. Now, when you are looking at a triangle, it is very important that you know how to find the hypotenuse, because if you can't find the hypotenuse, you're not going to be able to set your equation up. I can tell that 10 is my hypotenuse because it is the side opposite of the right angle. So the small triangle is missing a leg. I write out my equation and follow the steps to solve it. The missing length of b comes out to be the square root of 75. Sometimes it's okay to leave your answer in square root form, and that's exactly what I'm going to do for these two examples. Now that I've solved the small triangle, it's time to solve the large triangle, and to give myself a little bit of room, I'm going to cut off my answer to the small triangle. Once again, I draw the large triangle separately. This time, my hypotenuse is the variable a, because again, it's the side opposite of my right angle. So this triangle is missing its hypotenuse. I write in my two leg values and solve the equation. Calculating 20 squared may seem like a pain, but it can be simplified. I know that 2 times 2 is equal to 4, which means that 20 times 20 must be equal to 400. The missing length of a comes out to be the square root of 425. Looking back at it now, this problem may have looked complicated, but it was two problems that were kind of smushed together. One problem was a missing leg, and one problem was a missing hypotenuse.
That's it. That's the basics of the Pythagorean theorem so far. All we've looked at are the three main problems that it solves, which is the missing hypotenuse, the missing leg, and of course identifying the right triangle. Almost all Pythagorean theorem problems, no matter how tricky they are, almost always boil down to those same three problems. You just kind of figure out which problem you're looking at. In the next video, we're going to look a little bit more at the number theory of this stuff, okay? See you next time. Bye.